The first derivative test. This is a technique for finding maxima, minima, and function tendencies such as increasing or decreasing. Maxima and minima is simply plural from maximum and minimum. So here's a typical graph of a function. This one would have a local maximum here, a local maximum here. This one would actually be the absolute maximum because it's the highest the function goes. And this is a local minimum. It does not have an absolute minimum because it tends to go down indefinitely. The derivative of a function at a particular point gives the slope of the function's tangent line at that point. This is the slope of the function at that point. As a quick example, f of x equals x cubed as a derivative of 3x squared. This is using the power, the derivative of a power, x to a power. It would be 3 times x to the 3 minus 1 squared. At x equals 2, the derivative is 3 times 2 squared, or 12. Now that's the slope. The positive derivative indicates a function is increasing. A negative derivative indicates a function is decreasing. A maximum of a function in a neighborhood, about the point at which it occurs, is called a local maximum. A minimum of a function in a neighborhood, about the point at which it occurs, is called a local minimum. Now, if a function is continuous, there are two ways to go from a positive slope to a negative slope. One must go through a point where the slope is 0. How else are you going to go smoothly from a positive value to a negative value without going through 0, which would be at a local maximum? See, the function would be going up, then it would be going down. That would be the criteria for maximum. Or through a point where the derivative is undefined, and we'll make that a little clearer as we go on. Likewise, for a continuous function going from a negative slope to a positive slope, doesn't just go through a slope of 0, which would be at a local minimum, or through a point where the slope is undefined. Now, a little word of caution. It is possible to have a 0 slope other than at the maximum or at a minimum. An example of this is f of x equals x cubed. There's a 0 slope at 0, 0. When a function is at x is 0, f of x is 0. But that is neither a maximum nor a minimum. So we're finding tools to help us find maxima and minima. Likewise, it is possible to have an undefined slope other than at a maximum or at a minimum. An example is a derivative is undefined for f of x equals the cube root of x at 0, 0 due to a vertical slope. So actually we don't really call it a slope, but the tangent line is vertical. So now we'll look at 3 examples. The first one, we'll find a local maxima and minima of f of x equals x cubed plus 3x squared minus 9x plus 5. First thing we want to do is take the derivative. So the derivative of our function is 3x squared plus 6x minus 9. The derivative of a constant is 0. The derivative is 0 when 3x squared plus 6x minus 9 is 0. So we factor out the 3 and we factor. And so we now have set each factor equal to 0. 3x, x plus 3 equals 0. Gives us x is negative 3. And x minus 1 is 0. Gives us x equals 1. These are the values for which the derivative is 0. And they're called critical values. These are values we want to investigate. So we're going to pick a point left of the first 0, negative 3, going left to right. That's the first one we get. And we're going to evaluate our derivative at negative 4, I picked. Just to keep the number reasonable, you don't want to pick a number like 2,137 and 2/3. So 3 times negative 4 squared plus 6 times negative 4 minus 9 is greater than 0. That's all we care about. It's positive. So the function is increasing. Now we pick between 0 and 1. 0 is a real good number. That leaves us a negative 9, which is less than 0. The function is decreasing. And now we'll pick to the right of 1. We'll pick 2, relatively small number. And we'll get 3 times 4, 12, plus 6 times 2, another 12, 24, minus 9. That's positive. That's all we care about. So the function is increasing to the right of 0. So our function is increasing, decreasing, increasing again. That tells us a lot. The result is there's a local maximum at x equal negative 3 and a local minimum at x equal 1. Since the graph of the function goes to infinity to the right and to negative infinity to the left, there's no absolute maximum, nor is there an absolute minimum for this particular function. We don't have to have an absolute maximum, and we don't have to have an absolute minimum. When the derivative is undefined, there's also a need to investigate points at which this occurs. If a function is defined at a point where the derivative is undefined, you certainly want the function to be defined there. There are two possible ways in which the derivative would be undefined. The tangent line is vertical, there'd be a problem, and there is a sharp point in the function's graph. That means it would not be differentiable at that point. So we're going to take an example, f of x equal to cube root of x squared. This is going to be graphed going down and then going back up with a nice little point at the bottom. Kind of like perhaps a value of x, but it's a little more complex here. The derivative is undefined at x equals 0 due to the sharp point on the function's graph. You may think you have found the derivative, but it does not exist. Here the function is continuous through x equals 0. So the derivative is 2/3 x to negative 1/3. Actually, the derivative would not exist in this case because we'd be dividing by 0. So we'll investigate what's happening left and right of 0. Let's pick x equal negative 1, and we come up with a negative expression. It means the function is decreasing. Pick x equal 1, we get a positive expression, which means the function is increasing. If it's decreasing, then increasing, we have a relative minimum at x equals 0. And in this case, it's also the absolute minimum. Our next example is f of x equals x cubed. take the derivative of x cubed, and we get 3x squared. The derivative is 0 at x equals 0. For any negative value, the derivative is positive. The function is rising. And for any positive value, the derivative is also positive, which means the function is rising. This function is always increasing and has no maximum nor minimum, even though our first derivative is 0 at x equals 0. So that is only a clue as to where to investigate, and you still must